Hello student, hi, good evening. So today we are going to see the problem of transient circuit when we on and off the switch periodically, okay, periodically for the DC signal. Okay, so that is what the problem. Let's see here. My problem is what I have one voltage source of, let's say, 1 volt of voltage source. I have 1 volt of voltage source and I'm going to take here one switch. Okay, so this is my switch and this DC signal is my DC signal. I'm just connected this to low pass filter, RC low pass filter. Okay, so this is my low pass filter. This is my low pass filter. And now this is my, let's say, this is my 50 kilo ohm and this is my 10 microfarad of capacitance, and I want to find here the output voltage V0 of T. Okay, when this switch, if you see, when this switch is on, my switch is on at time t is equal to 0, then at 2, 4, 6 and so on, and my switch is off for time t is equal to 1, 3, 5, 7 and so on. Okay, so this is what periodic switching is there. Okay, so now in case of this, I want to find my output voltage across the capacitor when I will apply this DC source voltage to the low pass filter. Then what will be my output voltage that we are going to see? Okay, so if you see, my switch is on for even number of time. Okay, so this is my, if you see, this is my even number of time and this is my odd number of time. Yes, odd number of time. So this switch is on for even number of time, 0 second, 2 second, 4 second, 6 second, and this switch is on for time t is equal to 1 second, 3 second, 5 second, 7 second. If we will see this, what waveform will get generated by this switch on and off. Yes, if you will see here, this is my 1 volt of supply at t equal to 0, it is on, switch will get on, then my supply will go to this low pass filter as 1 volt. Yes, at t is equal to 0, it will go to 1 volt, and then this will off at time t equal to 1, then it will go on, off like this. This is at t is equal to 0, on, t is equal to 4, then 6 and so on, and it is off at t is equal to 1, then 3, then 5 and so on. Yes, now this is for both for t greater than 0 and for t less than 0. Yes, t less than 0 also it is on and off for even and odd time. So then I will get periodic square wave pulse. Yes, periodic square wave pulse whose amplitude is 1 volt. Yes, whose amplitude is 1 volt. So this is actually the square wave form that has been applied to this low pass RC filter. So I am going to find what output voltage across the capacitor. Let's see how to find this one. Okay, so now we are confirmed that when we switch on and off for periodically, we switch on at even number of time, switch off at odd number of time for both t greater than 0, less than 0 and we will get one periodic square wave pulse of amplitude 1 volt and whose time period is this is 2. Yes, this is 2 and this is my 4. This is 4 and so on. Whose period is 2 second. Yes, so let's see. Now I will remove this portion. And I will replace this as a periodic square wave pulse of 1 volt. Okay, so now see here, I am going to rub this and I will apply here periodic pulse of 1 volt. So that is what the periodic transient. Yes, so periodic switching is there. So this means that this is nothing but this is my voltage source. Okay, so now this voltage source is of periodic square wave pulse of 1 volt amplitude, and here time period is with the time period of t is equal to 2 second of time period. Yes, 2 second of time period. So this is exactly the means of periodic switching. So now we are going to find the voltage across the capacitor. So let's see. Now if you see, first of all, we have to find the combination of sinusoidal functions here. Okay, so for that we have to go for Fourier analysis. From Fourier analysis, we will calculate the sinusoidal function. Okay, so in terms of harmonics. So let us first see the Fourier series expression for this square wave periodic pulse. Then after that, we will apply it to a low pass filter, RC low pass filter, 50 kilo ohm with 50 kilo ohm resistance and 10 microfarad capacitance. So let's see. This is actually here ground. As we know very well, without ground, there is no existence for the circuit. So let's see the Fourier series. Okay, so here also we are going to understand, we are going to also explain the concept of Fourier series. So as we have got the periodic square wave pulse of 1 volt. So this is my 1 volt of pulse, yes, and this is at time t is equal to 0, and this pulse is what for both minus infinite to plus infinite. Okay, so and this is my 0 time, it is on, then it will get off at 1, then it will get on again at 2, and so on. So means its time period is what? Time period is t is equal to 2 second. Time period is 2 second. So now we have to find the Fourier series expression. So Fourier series expression for this is nothing but, let's say, v of t is equal to what? V of t is equal to summation n is equal to minus infinite to plus infinite Cn e to the power jn e to the power jn omega naught t. Yes, so this is what Fourier series expression. So this Cn is the Fourier series coefficient. So Cn here is the Fourier series. Fourier series. Cn here is the Fourier series coefficient. Fourier series coefficient. Okay, so now I have to find this Fourier series coefficient, that is nothing but Cn is equal to 1 by time period t integration 0 to t into f of t, means function v of t is what? So this means f of t into e to the power minus jn omega naught t dt. Yes. Now I have to find this Fourier series coefficient. Yes, how to find that? See here, Cn is equal to what? Cn is equal to 1 by time period, and also we should know that time period t is equal to 2 seconds. So as we know here that omega naught is equal to 2 pi by t. So omega naught is equal to 2 pi by t. So then here omega naught t is equal to what? 2 pi. Omega naught t is equal to 2 pi. So here 1 by t integration. Here 0 to t, f of t is how much? 1 into e to the power minus jn omega naught t dt, omega naught t dt. Yes, now we have to integrate this. So then after that we will get what? Fourier series coefficient. Okay, so then we will put this here and we will get actual voltage. Yes, so let's see, this is 1 by t, this. Now we are going to integrate this, what we will get here. So now I'm going to rub this here. Okay, so let's see. Cn, that we got Cn is equal to 1 by t. If you see here, integration 0 to t, up to what? It is 1. So because for total t it is up to t by 2, it is 1. So I can write here t by 2, 1 into e to the power minus jn omega naught t dt. So here Cn is equal to now 1 by t. Integration of e to the power minus j omega naught t is nothing but minus jn omega naught t divided by minus jn omega naught. Limit is 0 to t by 2. Okay, so then after that what we will get here? Cn is equal to, I am going to rub this also. What we will get here? Cn is equal to, take this outside, 1 by jn omega naught t, jn omega naught t. Here inside bracket put the upper and lower limit, that we will get 1 minus e to the power minus j and omega naught t by 2. Yes, t by 2. This I will get here after putting the limit. after putting the upper and lower limit, j n omega naught t by 2. As we know very well that omega naught t is equal to what? 2 pi. Omega naught t is equal to 2 pi. Just put this omega naught t is equal to 2 pi here. What we will get? We will get Cn is equal to 1 by, here if you see j n omega naught t is what? 2 pi. So this is 2 pi n j. Yes, 2 pi n j, and this is what? 1 minus e to the power. When we will put omega naught t is equal to 2 pi, 2 get cancelled, we are left with j n pi. Yes, j n pi. So this is what Fourier series expression. So again, you can note down this, and I'm going to rub this here. So after that, what we will get here? We will get Cn is equal to what? Cn is equal to 1 by j 2 pi n 1 by j 2 pi n. This is j 2 pi n. Here if you see 1 minus 1 to the power what? N. So because e to the power j n pi, e to the power minus j n pi is nothing but minus 1 to the power n. So now see here, Cn is equal to, if you see for n odd, if we will put n odd, if we will put n odd, then what we will get here? Odd means minus become plus, means 2. So it become 2 by j, it become what? 2 by j 2 pi n. Yes, for n odd, and it becomes 0 if you will put n equal to even, means 1 minus 1 0, it becomes 0 for n even. Yes, n even. If we will put n is equal to even number, it becomes 0. Yes, so this is for n even. Now see what we got. Cn is equal to, finally Fourier series coefficient that we have got here is what? Cn is equal to what? Cn is equal to, finally we got Fourier series coefficient as Cn is equal to, here 1 by j pi n, when j pi n for n even and odd, and we got 0 for n what? For n even. Okay, so for n even we got 0, for n odd we got 1 by j pi n. So this is what Fourier series coefficient. Now see here, we are going to find the Fourier series expression or the square wave pulse. That is nothing but here v of t is equal to summation n is equal to minus infinite to plus infinite. Cn, what we got? Cn here is, we got Cn here 1 by j pi n e to the power j n omega naught t. Yes, here my omega naught is what? Omega naught is 2 pi by t. T is what? 2, so means it is what? Pi radian per second. Yes, omega naught. So if you see here, this is what? For odd. Here n is my odd. Yes, n is my odd number. Yes, this is my, n is what? Here odd number. N is my odd number. Yes, n is my odd number to infinity, 1 by j n pi e to the power. Okay, so j n omega naught t. Now see here, when we will put this as here, v of t is equal to n value. When we start putting n value for odd number, for both positive and negative side, what we will get here? We will get here, if you will see, n is equal to 1 e to the power e to the power j omega naught t minus e to the power j omega naught t. So j down is there, we have to adjust this, and we will get 2 by pi at outside. And inside we will get sine omega naught t plus sine 3 omega naught t plus dash. Okay, so this is what Fourier series expression that we have got with n harmonics. Yes, so that is what finally what we can write here. We can write this v of t that we have got here is, finally we got the v of t is equal to 2 by pi summation and odd, summation and odd to infinite sine n omega naught t, sine n omega naught t, where n is what? N is odd number, n is odd. This is sine omega naught t plus sine omega naught, sine 3 omega naught t plus sine 5 omega naught t plus dash dash, so on. So this is what finally we got the Fourier series expression, sinusoidal and harmonic expression for this periodic pulse that we have applied to the low pass filter. Okay, so where omega naught is nothing but pi, that we have got here pi. So I can write, finally I can write what here. Let us remove this totally. What we got, that we have seen. Now what we have got here, we have got the voltage V of t is equal to what? V of t is equal to summation and odd to infinity. This is sine here, sine and pi t, yes. So this is our final voltage, final and harmonic sinusoidal voltage that we have applied to the RC low pass filter. So then this is what here, this is my voltage source of V of t, which before periodic switching it was 1 volt, after periodic switching it become this volt, yes, this much volt, with sinusoidal and harmonic, odd harmonic, where n is what? Odd here. Okay, so that I have mentioned here, odd. So now this is now connected to what? RC low pass filter. This is connected to RC low pass filter, yes, RC low pass filter. Now here we have to find what? Output voltage V naught of t, where my R is what? 50 kilo ohm and capacitance is what? 10 microfarad. Yes. So this is what the problem that we have solved for this portion. Yes, now we are going to find this output voltage across the capacitor. Okay, so where my input voltage is this one. So see properly here, this RC filter is what? This RC filter is what? This is nothing but an LTI system or not? LTI. This is nothing but LTI system, means linear time invariant system. This RNC. So therefore this system is what? My LTI system, as we know very well. For an LTI system, whenever the input is sinusoidal, then the steady state output will also be sinusoidal. Okay, steady state output will be also sinusoidal with same frequency, except with same frequency with same frequency, but amplitude and phase may get vary. Yes, that we know very well, that for any LTI system, if my input is sinusoidal, then my steady state output will be also sinusoidal with the same amount of frequency, but the amplitude and phase we get vary. So that is what we know. Now first of all we are going to find its transfer function. From transfer function we will calculate the magnitude response and phase response. Okay, so then phase response for this frequency. So let's see how to calculate that one. This is input that we know very well here. Okay, so what we got the input, so this is my V of t, that V of t just here 2 by pi was there. Yes, 2 by pi was there, so just I didn't mention there. Okay, so please note it down. So this is 2 by pi and is what? Odd, and odd to infinity, and here is my sine and pi t, sine and pi t. Okay, so this is what actually that we have applied to the RC low pass filter. So this is okay. So now we are going to find the transfer function, which is very easy. How to find the transfer function? Let's see here. So this is positive, negative, and this is my RC, and this is my low pass filter, and this is my ground here, and this is V of t that we have applied. This is my R and this is my C. Okay, so where V of t that we have obtained as 2 by pi summation and odd to infinity sine and pi t. Okay, volt. So this is my input. Okay, so now how to find the transfer function? Let's see. Here is my output V naught of t. So writing in as domain, so this R is what? R is 50 kilo ohm, and this C is nothing but this is 10 microfarad Okay, so now by applying voltage division rule across the capacitor, output capacitor, we get output voltage V naught of S in S domain as 1 by SC multiplied by input voltage in S domain divided by, this is what, R plus 1 by SC. So from there we will get V naught of S is equal to what? Is equal to, so this is my V of S divided by 1 plus SRC. Yes, 1 plus SRC. So the transfer function that we got here, H of S is equal to V naught of S divided by V of S is equal to 1 by 1 plus SRC. Yes, this is my actually transfer function that we have obtained for this system. Okay, so now we are going to see this in frequency domain. This is an S domain, so we are going to find the frequency response and phase response for this, magnitude, frequency and phase response for this. What we got, 1 by 1 plus SRC, where RC is nothing but, if you see here, RC is nothing but, R is what, 50, 10 to the power 3. So let's see, we will calculate it in next step. Okay, so I am going to rub this here. Okay, so this everything that we know, input voltage is this one. So I am going to rub this again. So we got what? Got transfer function as, we got transfer function as what? Transfer function that we got as 1 by 1 plus SRC, where my RC is equal to, R is what? 50 into 10 to the power 3, C is what? 10 microfarad minus 6. So my RC will be equal to, if you see this 5, this is 4, this 4, 5, this is 0.5. Yes, this is nothing but 0.5 second. RC, time constant. Yes, so therefore my transfer function will be equal to what? 1 by 1 plus 0.5 S. Yes, which is nothing but here 2 divided by S plus 2. Yes, so this is what the transfer function that we have obtained. Okay, so now again I am going to rub this. Now we are going to find the magnitude and phase response for this. So what is my magnitude and phase response? As we have obtained, H of S is equal to 2 by S plus what? S plus 2. So my frequency response H of omega, that will be equal to 2 by 2 plus j omega. Here the magnitude response will be H of omega, magnitude is equal to what? 2 divided by square root of 4 plus omega square. Okay, 4 plus omega square, and my phase response will be equal to what? H of omega, that will be equal to minus tan inverse omega by 2. Yes, so this is my magnitude response and phase response. Now I am going to find the magnitude and phase response at given input frequency. My given input frequency is nothing but n pi. Okay, so again I am going to rub this. We are going to find the magnitude and phase response at given input frequency. My given input frequency is nothing but n pi. Yes, n pi. My given input frequency, n pi radian per second. Yes, that we know, radian per second. So therefore here magnitude H of omega at input frequency omega is equal to n pi, that we get here as 2 divided by square root of 4 plus n pi whole square. So this is my magnitude response at the given input frequency, and angle phase response for given low pass filter at given input frequency is what? H of omega is equal to, here at omega is equal to n pi, this will be equal to minus tan inverse omega. So that was omega by 2. Yes, minus tan inverse omega means n pi by 2. Yes, n pi by 2. So this is my phase response and magnitude response at given input frequency. Yes, where my input was what? V of t is equal to what? 2 by pi, that we have obtained. Summation n is what? Odd. Summation n odd to infinite sine n pi t. Yes, n pi t volt. So at input frequency we have found this. As we know very well that the steady state output voltage for given sinusoidal input voltage passing through RC low pass filter, which is a LTI system, is obtained as, let's see what will be the final output. So that is nothing but, so this is here, I am going to write the final output that we will obtain as what? Final output is nothing but here, let's see, let me write here, V naught of t is equal to what? Input voltage magnitude. So this is what here, Vm into magnitude response at input frequency, okay, input frequency, then into what? Into sine input frequency plus phase response h of omega at input frequency. Yes, now we are going to put here in this expression all the known value. So that is nothing but V naught of t is equal to what is Vm? Vm is nothing but 2 by pi. What is my h of omega? This one, h of omega that we have obtained, 2 by square root of 4 plus n pi whole square, okay, n pi whole square, and here is my sine. This was actually summation. Yes. Okay, so no problem. Here I will write, this is summation n is equal to odd, n is equal to odd, okay, so odd to infinity, sine n pi sine n pi t, yes, sine n pi t plus here angle that was minus tan inverse n pi by 2. So here let me write clearly this, okay. So here this we got what? 2 by 4 plus n pi square. I am going to take this portion inside because it is what? It is the function of n. So all the function of n I am going to take inside the summation. Then finally we will get what? The final steady state output voltage. So that is what here, final steady state output voltage that we will get here as V naught of what? V naught of t is equal to 4 by pi, yes, 4 by pi summation n odd to infinite, here sine n pi t divided by square root of 4 plus n pi whole square. Yes, so let me write here angle also, plus angle was negative that we have obtained. So this is my angle minus tan inverse what? N pi by 2. Yes, so this was our final steady state output that we have obtained across the capacitor voltage. So that is what we know. This concept very well, we have explained. So we have seen this concept very well. Okay, so whenever there is a periodic switching, okay, in the circuit from the DC supply voltage, so then it will generate what? Periodic square wave pulse. So for that we will replace that source by periodic pulse, yes, periodic square wave pulse. Then after that what we have done? Then after that we found what? Fourier series expression for that periodic pulse. Okay, so in the form of sinusoidal and harmonic functions, okay, so which is odd harmonics. Then after that what we did? Then after that we just found the transfer function. Then after transfer function we found the magnitude and phase response. After that we found the magnitude and phase response at the obtained input frequency. Yes, then after that we found the output voltage, yes, across the capacitor, which is a sinusoidal voltage with the same frequency, but the amplitude is what? Different, and angle is also different. That we have already mentioned that the output voltage is also a sinusoidal voltage with the same amount of frequency, but the amplitude and phase may get vary. So that is what the type of problem based on the periodic switching. So thank you very much.